The purpose of this lab was to model and predict the motion of a mass attached to a spring and its oscillations up and down, and then model the changes in energy using tracker and code. I compared the predicted motion from the computational model and the observed motion, and they were very similar. So the modeled changes in energy should be very accurate to the actual motion, and we can see that in the energy, and we can see that the energy principle is satisfied. I did this using Newton's second law and the formulas associated with the energy principle. Newton's second law, the equations to the right, are useful in computing the changes in motion, position, and velocity, and relating it to force. Applying the position update and velocity update formulas is how we can predict the motion of an object in a computational model. The spring force formula was also very useful for this lab, and if the only forces in a system are the force of gravity and the force of the spring only in the y direction at time equals 0, they can cancel out, so you can solve for L and the other variables in the equation. You can use the formula for the period t of an oscillation to find the spring constant, which can then be plugged into the spring force formula to find the other desired values. The energy principle was a very important piece of this lab, since it lets you calculate the change in energy of a system and equals the work done by the surroundings plus the transfer of energy between the system and the surroundings. But if the surroundings have no effect on the system, then the principle shows that the total change in energy is 0. This means that the sum of all the different energies in a system is 0. For the system in this lab, there was kinetic, gravitational potential, and spring potential energy. And these are all the equations I used below. So in this experiment, the system is the ball, spring, and the earth. The surroundings are everything else in this scenario. The surroundings have no effect on the system, so the overall change in energy is 0. The initial conditions for the lab are t equals 0 and position is negative 0.15115 and negative 0.635. And the velocity is at rest or 0. And the top of the spring is the origin, and its initial length is 0.7 meters, and the mass of the object is 0.402 kilograms. And so in the experiment video, a mass in a spring is released and moves in a circular path while the spring starts oscillating up and down. I tracked this motion in Tracker to see the x position and y position oscillations and the path of its movement. Then I made a computer model of the same Earth mass and ball system to predict what the motion would look like. I also calculated the different energies in play, and how they changed throughout the motion. And so here's the first part of the code, and through coding and calculations, I was able to calculate the initial length of the spring and the different values needed to calculate the force and energy of the spring. I then used the formulas for the different kinds of energy present in the system and the system's initial conditions to get their initial values. Now that the initial conditions were set, I used a while loop to continuously update the necessary values for each data point. Using my knowledge about forces, gravity, and the spring force equation, I found the net force. Then, with the net force, I used Newton's second law to update the mass's velocity and then position. Then I updated the spring-related constants with the new position so I could recalculate the necessary energy values and find how much they changed from the initial to the current. I then added all the changes in energy to get the total change in energy, which in this case is 0. I also used the code to make graphs that showed the difference in motion between the tracker data and the predicted motion, and one that showed how each type of energy changed over time. And that's the graph that is shown right here. Each line is a different type of energy, and the orange line is the sum of all the energies. It's the total energy, and it's on the x-axis at 0, which proves that the energy principle is true here, since we predicted that if the surroundings had no effect on the system, it would be 0. And here's what the output model looked like of the spring and its motion. And here are the models for comparison. The tracker data is red, and the blue is the model, and it shows how similar they are. The models in the previous slide show how similar the predicted model and the actual tracked motion of the object are, since it compares the predicted y direction and x direction motion with the tracker x and y position data. The lines in each graph are almost identical, showing that our prediction model is almost 100% accurate. I predicted that the total change in energy would be 0 due to the energy principle, and the energy prediction graph shows that the sum of all the different energies is 0, so my prediction was correct. In conclusion, this lab shows us how the energy principle works and how, since there is no effect on the system by the surroundings, the change in energy is 0. It shows that I can model and predict the motion of a spring oscillating up and down and swinging in a circle through applying Newton's second law of the spring force equation and other physics formulas discussed earlier. A source of error could be human error and marking of the points in the tracker and having time between each point. Another source of error would be how the surroundings have no effect on the system in the computational model. When in the real world, they do, since there is air resistance and changes in heat. So for the what does it mean questions? Yes, the energy principle is satisfied since the sum of all the internal energies is equal to 0. We said that there is no non-negligible effect on the system by the surroundings, which means that the change in energy of the system should be 0, as the output graph shows. For the second question, using the oscillation formula discussed earlier in the tracker data, I found that the oscillation period for the x position data is about 1.63 seconds, and the period for the y position data is about 1.53 seconds. These numbers are exactly 0.1 apart, and they are very similar, which is good since they are for the same object movement, just different directions. The slight difference is probably due to the human error when I clicked the points for tracker.